Good evening. This is a lovely auditorium, and the mic works and everything. I'm Lisa Story-Lombardi. I'm the director of the Las Cumbres Observatory. And first I want to thank the museum for hosting us in this lovely space so we can tell you about some of the science and technology that we're really excited about. If you don't know who the Las Cumbres Observatory is, our headquarters is in Goleta on Cortona Drive, but our network is a global robotic network of 25 telescopes. We are all around the world, and we primarily we're all at professional sites. All of our telescopes are at professional observatory sites. And one of the reasons LCO was built is with the technology that was available that you could set this up and run it robotically. It's actually run from the Amazon software in the Amazon cloud that can reschedule the entire network, all of the telescopes, every 2 to 5 minutes. So scientists and educators can request via their computer observations, and when something in the sky changes, we can get a telescope. We should have a telescope in the dark that can observe it now and then watch it change. So one of what you're going to hear about tonight is a survey, science from a survey telescope that's just been commissioned in Chile. And I would like to introduce R.Street, one of our senior scientists, who is going to tell you a little bit about the Rubin Observatory and then introduce our speakers.
Thank you so much. Thank you very much, Lisa. And hello, everybody, and welcome to tonight's event. I'm so glad you were able to join us. I hope I'm not causing ear-splitting feedback here, but... So, I'd like to talk tonight about a fantastic new experiment that is going to start and that is going to revolutionize many areas of astrophysics. So, this project has been over a decade in the planning, and it only recently entered commissioning. And over the last couple of months, we got our very first glimpses of the very first images that this great machine can produce. Some of you may have seen some of the beautiful images in the press. Tonight, we'd like to take a closer look. We'd like to dive beneath the beautiful pictures that you've already seen and take a closer look at some of the science that Rubin will explore. Now, our team at Las Cumbres Observatory have been closely involved with the development of this project actually since its very early days. And so I'd like to kick off the event with an introduction to the project itself, and then I'll introduce you to a series of 3 terrific scientists from Las Cumbres Observatory who are going to take a deeper dive into the different science cases that they are going to explore with this great experiment. So, what is Rubin Observatory? Rubin is a brand new state-of-the-art telescope situated in Cerro Puchón in Chile. This is a very high altitude, very dry site with some of the most stable atmospheric conditions in the world. So it's ideal for astronomy. Inside this custom-built observatory building is the Simony Survey Telescope. This is a huge facility. The telescope has a primary mirror that is 8.4 meters or 27.5 feet, and that is the size of 2 typical cars parked end to end. This huge light collection area allows it to see very distant objects, very faint objects far away in space. But most unusually, the unusual optical design of the telescope means that it, at the same time as having a big collecting area, it also has a very wide field of view. And as you can see from this video, despite this enormous size of this machine, it's designed to move very, very quickly and slew to new positions in the sky very quickly, and that combination makes it the ideal survey machine. Imaging that huge field of view is the largest digital camera ever built. Now, on the left-hand side here is a picture of the camera while it was being built here in California at the Stanford Laboratory. And you can see the person standing next to the camera to get a sense of scale. Now, this camera is not a single image sensor. It's actually a mosaic of 189 CCD detectors, similar to what you have in your cell phone, but much larger. And that is the equivalent of a 3,200 megapixel camera. This camera is now mounted on the Simony telescope in Chile, where it has a field of view of 9.6 square degrees. Now, that's huge in astronomical terms, but it is quite difficult to visualize. So if you picture the size of the full moon as you look to it on the sky, the Rubin camera can image a patch of sky 7 times as wide as the width of the full moon in a single exposure. So in just a few months, Rubin Observatory is going to begin the Legacy Survey of Space and Time, otherwise known as LSST. And it's this project that is really going to change astrophysics. Rubin will continuously survey the entire southern sky for a decade. And it won't just visit each patch of sky once, but dozens of times. And it will take images in 6 different color filters. That will create not just an unprecedented time series of data, it will effectively give us a color movie of the night sky. And although there have been previous astronomical surveys that have done repeated images over a period of time, none of them will have been able to cover the whole sky to the same resolution or to the same faintness as Rubin will. And so this is going to allow us to explore everything that moves or changes in brightness in the night sky over the next 10 years. Now, a huge camera and a rapid survey also adds up to a huge amount of data. Rubin is going to generate 20 terabytes of data every night it operates. So over the whole 10-year survey, that obviously adds up, and that's 60 petabytes of image data, and that's just the raw data products. That's not the reduced data. So, crucially, Rubin will also have a state-of-the-art data processing system. It will analyze every single frame that it takes in real time, and it will detect every object within each frame. That will allow Rubin to build up a colossal reference catalog of everything that it can see in the southern sky, including millions of objects that were so faint that we've previously never seen them before. Now, by comparing the detections from one image with the detections of the next one, you can also tell whether something's changed in between. And so we look for something that has changed brightness or changed position. And when it does, Rubin will be able to issue automatic discovery alerts to the whole worldwide community within seconds of shutter close. And that combination makes Rubin an awesome discovery engine, and it allows astronomers to follow up all of those discoveries in real time. And that combination is what's going to be so transformative for virtually every area of astrophysics. Now, the expected catalogue that this will produce is awesome in scope. 20 billion galaxies, 17 billion stars, of which 10 million will go supernovae. And within our own solar system, 6 million objects. So this video compares one of the deepest and colored surveys that we have taken to date with some of the earliest image data that is coming from Rubin Observatory. And you can see how many more images and how many more stars the Rubin will be able to see. Now, this image was released as part of the recent first look at data from the Rubin Observatory, but I don't really think that this does it justice. So I'd like to take a moment just to really take a look at some of the beautiful new data that was released just about last month. I think that really gives you a sense of awe in what this telescope is going to discover. And now it's not going to stop playing. Still, it's a beautiful video. So the data that Rubin will take will transform virtually everything in astrophysics, but the observatory was designed around particular design goals that was similarly grand in scope. Its whole visible sky survey will help us to understand the nature of dark energy and dark matter. It will complete the census of the objects that we know of in our own solar system. It will detect transient and variable phenomena of all kinds, even right down to the rare and hard to detect phenomena that are that we otherwise wouldn't know about. And it will map the structure of our own Milky Way galaxy and give us a wealth of information on its evolution. And we have talks tonight that will take a deep dive into the detail of all of the topics. But data from Rubin alone won't be enough to fully understand the nature of many of the discoveries that it makes. The survey's role is really as the discovery engine, to discover stuff that moves or changes brightness and let the world know about it. To fully characterize those discoveries, we need additional data from other observatories, and that's where LCO and our partner observatories come in. So although Rubin is just about to start operations, LCO staff have already invested years of work preparing for this survey. And tonight we're going to hear from several of our excellent early career scientists, each of whom specializes in a different area of astrophysics. First up, we'll hear from Kruszynska, who studies galactic science and in particular microlensing. Then Joseph Farah will talk to us about supernovae and other explosive transients. And Catalyst fellow Carrie Holt will tell us what Rubin has to discover in our own solar system. And then at the end, I'll invite all of our speakers up back onto the stage where we can answer your questions. So hopefully after tonight, you will be keen to learn more about Rubin. So before we dive in, I'd like to share how you can do that. The best place to start is rubinobservatory.org, where you'll find some of the early data that's released together with some fantastic interactive apps that are a really beautiful way to discover more about the project and more about the science. And so with that, allow me to introduce Kruszynska, postdoc from LCO.
Thank you for introducing me, Rachel. Hello, everyone. My name is Kruszynska. I'm a postdoc at Las Cumbres Observatory. Today, I would like to talk to you about all the amazing galactic science that Rubin Observatory is going to deliver. So Rubin is going to observe the galactic plane visible from the southern hemisphere, which is visible in this picture as this large dusty area spanning across the night sky. We can visualize this better by projecting the whole Milky Way onto a map with the Milky Way in the center. which is exactly what has been done in this picture. We have the Milky Way in the galactic plane in the center of the image, and then the exact center of the image is an area called the galactic bulge. And now we can also overplot the number of visits Rubin is going to do during its 10-year-long mission. And in this plot, the darker the color is, the bluer, the more visits it's gonna get. So the most frequently observed fields are going to get over 100 visits per year. Most of the galactic plane, which you can see in here in the center, is going to get anything between 10 to 1,000 visits over 10 years. As Rachel mentioned in her talk, mapping the Milky Way is one of the 4 science pillars of Rubin Observatory. At the end of the 10-year mission, it is going to observe 17 billion stars. That is 10 times more than the current surveys have ever seen, and around 1/10 of the total amount of stars in our galaxy. Rubin is also going to observe much fainter and more distant stars than previous missions could. And it is going to see stars that are 10 to the 20th power, fainter than the human eye can see, which is 10 with 20 zeros. It is also going to observe in different filters at different times, producing a 10-year-long color video of the sky. In this particular video, which was produced for the First Look event, you can see stars across the area observed by Rubin that have variable brightness. And the astronomers very originally called them variable stars. For this particular video, a certain type of variable stars was chosen that can change their brightness between 10 to 30% in the span of minutes to hours. Such data will allow us to detect many previously unseen variable stars and transience phenomena. And I'll just let the video play for you. It's very nice. And all the little circles pulsating, and here are the variable stars visible in that field. Okay, now I can move on. There are a lot of things we can see in our galaxy, such as variable stars that I have shown in the previous slides. However, there are also a lot of objects we cannot see because they are too faint, too distant, or they don't emit any light at all. These objects are the subject of my area of studies, and Rubin will observe a phenomenon that will help us find those our galaxy's hidden populations. These hidden populations that are particularly interesting for me are remnants of stellar evolution. This is the end stage of a star's life, and these objects are things such as black holes, neutron stars, or white dwarfs. In particular, I am looking for solitary black holes. Theory predicts that there are millions of isolated black holes in our galaxy. Currently, we know over 60 black holes that have companions, and they are consuming those companions, and thus they can emit light. But we have found only one solitary black hole flying through space because they are so difficult to detect. I study a phenomenon that can help us uncover such objects, which is called gravitational microlensing. It is an effect of Einstein's general relativity, where a massive object deforms the space-time around it. As it passes the line of sight between us and a distant star in the Milky Way, it is going to create 2 or more unequally magnified images of the source. And as the lens is moving, wait, sorry, I have a technique for this. Haha. As the lens is moving in and out of the alignment, the total magnification of the source changes, and then it creates a very characteristic change over time, which can be hardly reproduced by any other phenomenon. Traditional microlensing surveys have devoted their time to observing the galactic bulge, which is the area around the center of the Milky Way. But more recent surveys have started to observe the whole galactic plane, and Gaia was one such survey. Gaia was an European Space Agency mission that was observing the whole Milky Way, and I have been working on this data, on the data from this mission, and have me and my coworkers have found many microlensing events happening all across the galactic plane, which you can see in this animation on the right-hand side. Each little blink is one microlensing event happening. Gaia was a pathfinder, a pathfinder, but it could not go as deep as Rubin. Rubin is going to observe thousands of such events per year, and it's going to see them across the whole Milky Way visible from the southern hemisphere. Rubin is going to be a wonderful discovery machine for such events, expanding the work of precursor surveys, which were limited by how faint and how wide they could have gone. And this will give us a unique look into the galaxy's hidden population in a wide range of stellar environments. However, I could talk about microlensing the whole day, and there's a wealth of other galactic plane science Rubin is going to deliver. And one of them is shown in this image, which was one of the first images released by Rubin. These are Trifid and Lagoon nebulae. They are prime examples of stellar nurseries in our galaxy. These stellar nurseries are called by astronomers star-forming regions. These are massive gas clouds in which local changes happen, and this causes local overdensities of the gas, and this gas starts to collapse into a star. This can happen in many places in such a cloud, and over hundreds of thousands of years, multiple infant stars will start forming in here. Rubin is going to observe many star-forming regions across the whole galaxy, across different conditions, which is going to tell us how stars form and under what conditions. However, Rubin is not only to give us such an amazing picture, it's going to give us a whole movie. This means we will see how infant stars change their brightness over 10 years. Such objects are known as young stellar objects. These are objects that just started collapsing from a gas cloud into a ball of gas, and we call them protostars. Or they can be a ball of gas that have already collapsed, but they haven't started burning hydrogen in their centers, which we call pre-main sequence stars. These are often enveloped or surrounded by gas and dust, which you can see on the right-hand side in the big image. In the center, we have a young stellar object, which is shining brightly, and then all around it you see like this dust and gas. And if we looked right into the center of this bright spot in the middle, we would see something that you can see here in the right corner. And that is in the center we have a young, young infant star surrounded by a protoplanetary disk, which is a disk of gas and dust from which the exoplanets can form. However, these objects do not have constant brightness over time. They change it from hours to years due to interactions with the enveloping gas. Shown on the right-hand side is the brightness of a young stellar object changing its brightness over nearly 10 years. You can see small changes and little outbursts and dimming happening at the timescale of days. But also there is a large change happening over years where the object is getting very slowly brighter, and then you see this large dip, which is a large dimming, which has happened. Rubin is going to observe such young stellar objects across a long period of time in different colors, creating a wonderful baseline for detecting outbursts, dimmings, and changing color. When these young stellar objects are formed in the same gas of cloud and they started burning hydrogen, they become fully fledged stars. And they form something which is called an open cluster. Such clusters consist of tens to a few thousand of stars, and they are loosely gravitationally bound, which means that they can lose members while an open cluster is orbiting our Milky Way. One very well-known example, which you can observe from the northern hemisphere, are the Pleiades. And Rubin is going to observe very faint and low mass members of such open clusters that we have never been able to detect before. Come on. On the other end of the age spectrum, we have globular clusters. These are clusters of very old stars, which are strong gravitationally bound. They contain tens of thousands to a few million stars that are more concentrated in the center of the cluster, which you can see in here. One very known example is Omega Centauri cluster. Rubin is going to observe very faint but highly resolved globular clusters across the galactic plane. We will be able to measure the distances and locations of the clusters around the galaxy, which will help us understand merger history of the Milky Way. To measure the distances to globular clusters, we are going to use pulsating stars. And for this particular case, we want to use stars that are older, reaching the end of their nuclear fuel. These stars are pulsating, which means they're getting bigger and smaller, and cooler and hotter, which at the very predictable periods in a regular way. Because they're also getting hotter and colder, it means they change color. And this allows us to use them as ideal candidates for measuring distances in space. We will allow us to measure a huge population of such stars across the galaxy and our closest companions. It will give us a look into the different substructures of the Milky Way, such as the galactic arms, the galactic bars, and surrounding satellite clusters and galaxies. And Rubin is going to discover many, many more types of variability in the galactic plane, and I could talk about this for hours. But the main takeaway message is that Rubin is going to give us a wealth of science across the whole southern galactic plane. We will get a 10-year-long color video of the Milky Way with fainter and more distant stars than ever. And I am very excited to be a part of it. And now I will leave the stage to Joseph Farah, who will talk about the things outside of the Milky Way that Rubin is going to observe. Thank you very much. Come on, Joe.
Great job. Okay. Sweet. Okay, so hey everyone. I'm here to let you all in on the exciting impact that Rubin will have on extragalactic science, which is my field. So extragalactic science refers to pretty much anything that happens outside of our own galaxy, the Milky Way. This includes extragalactic supernovae, which are the death of massive stars, but also kilonovae, which are the explosive mergers of two neutron stars. So we'll talk about supernovae and kilonovae today, but extragalactic astronomy is a huge category and includes many other things that go boom in space. And Rubin is going to be a game changer for all of them. But how? So we're going to be having a conversation with the universe through Rubin. And I use conversation here as an analog for how we will interact with this amazing observatory. And just like a conversation with another person, our interaction with Rubin will have three parts: listening, following up on discoveries, and responding with our own observations and triggers. So let's start with step one. Listening to Rubin. Rubin's going to be an immensely powerful discovery engine, and our greatest utility from it will come by listening to its alerts for new activity in the universe. So what exactly are we listening to? So Rubin is going to record basically the entire southern night sky every few nights, and it's going to look for tiny changes in every star and galaxy in its gaze. For example, when a supernova appears in a galaxy, it shows up as an entirely new star that wasn't there before, which sounds like it should be really easy to see, right? Well, so here's a challenge. This is a before and after of a picture of the closest supernova in the last decade, 23 IXF. Can anybody tell where the supernova is? And no one from LCO is allowed to answer. Right. Okay, so that's exactly right. That's where 23 IXF is. But it's not the easiest thing in the world, right? And this is the easiest possible scenario where you have a huge galaxy right in your field. Rubin's is going to look more like this, right? So in this image, every single dot basically is a galaxy just like the one before. And this is just 1/20th of one of Rubin's fields. So Rubin has this incredibly advanced subtraction and source extraction software that allows it to find every single variation of every single object that it can see. And what that's going to amount to is literally tens of millions of transients monitored every single night. And of those, tens of thousands will be new supernovae. And that's crazy because to date, we've only discovered around 10,000 supernovae ever. So it's really hard to wrap your head around these numbers and why having so many supernovae is useful. So to date, we have discovered around 10,000 supernovae. Rubin's going to discover 10 million, and that's a lot. But also, I know, when numbers start getting bigger than 1,000, we kind of lose our ability to understand how big they are. So I'm going to try to give you some context. So we've discovered over decades and decades 10,000 supernovae, but Rubin is expected to find that many in basically the first month of its observations. That's such a game changer. So let me bring you in on some numbers that this will be relevant to for my specific subfield of astrophysics. So I study very rare subclasses of supernovae. So we have 10,000 to 20,000 known supernovae, but the ones that I work on, we only have 20 or 30 examples of them. As physicists, we're interested in understanding physical processes, and I have this plot that will kind of help visualize this. So we're interested in understanding physical processes, and physical processes can often be expressed as a function between two quantities. So I have two hypothetical quantities here, x and y, and they have this relationship which is formed by this blue line. And that's what we want to learn about. We want to get the blue line. Now, if we get our hypothetical 30 supernovae, well, this pink line represents what our best guess would be with just 30 supernovae, and it's actually not that bad, right? With even 30 points, it's not perfect, but it's pretty good. We've gotten good at this. We can work with a very small set of objects. But here's what Rubin will do. So we will go, and this is not an exaggeration, we will go from 30 to more like 300,000 supernovae in this incredibly rare subclass. And so our estimations of physical processes go from rough guesses that are probably fine to approximations of the truth. And that's what Rubin is. If I had to pick what I was most excited about for Rubin, it would be this. It's a chance to see the truth of the universe kind of free of the sampling bias that every scientist gets beaten into them. Don't fall for these tricks. Don't fall for the low number of objects, misleading you. We don't have to worry about that with Rubin. Any kind of object you can think of, you're going to have 100,000 examples of them in a year. It's unbelievable. So unfortunately, our existing infrastructure is not really equipped to go from discovering 10,000 supernovae in a decade to discovering 10,000 supernovae in a week. So we had to make changes, lots of them. And some of these changes involved leveraging these tools in the astronomy community called brokers. And these are some example brokers on the left here, LSST, Antares, and LSST, and there's lots of them. Now, brokers collect all this huge amount of data, and then they give you information. They collect it all in one place, information like the distance, and it gives you all the data and classifies them based on the data using these really advanced machine learning algorithms. And so you can know early what's likely to be interesting and what isn't. So this screenshot here is from a broker that I use daily called LSST, and it shows the information and details on a rare supernova. So you can see it's got the name of the supernova up here and how far away it is, and this is its light curve, which Rubin is going to give us on the whole southern night sky. This down here is what I was mentioning, where it's classified this supernova based on an automated machine learning algorithm. And this is a little sneak peek at the kind of stuff Rubin will do. I mean, this is for a different survey, but it's the same principle. You have this image that has this new dot in it. When you subtract it from an old image that doesn't have the dot in it, you're left with the dot. And Rubin's going to do that for every patch of the sky it can see, and we're going to be able to collect it and all this information it's going to get in these brokers and learn all about these objects. So we're going to use brokers and tools like this to keep track of all the discoveries pouring out of Rubin, filtering out just the most interesting stuff and putting our own telescopes on them. Which brings us to part 2 of the conversation, which is following up on Rubin's discoveries. So how are we going to do this? So first, Rubin itself is going to be able to follow up on its own discoveries to some extent. So it'll survey the southern night sky around once every 3 to 4 days in 2 bands. So at the bare minimum, you'll have multiple filters worth of data for the entire southern night sky on a several-day cadence. For small areas of the sky, so these patches on this sky map here, these are the deep drilling fields, Rubin's going to return to these on almost a daily cadence. So for these small patches of sky, Rubin's going to, the analogy here is like drilling for oil, it's going to come back repeatedly and give us lots of high cadence data on just these tiny parts of the night sky. And in just 3 years, it will achieve the full 10-year survey depth in these regions. But what if you need more than just a couple days, and an observation every a couple days, and you're not in one of these tiny patches of sky? So what do? So many of us are part of these programs like Shadow, so that will fill in the gaps that Rubin leaves using other telescopes. So Shadow is proposed and run by us and many of our colleagues in the community, and we'll use existing hardware such as the Dark Energy Camera, or DECAM. This is the telescope that DECAM's in. It'll fill in the gaps between Rubin's visits to help us catch discoveries early. So it'll go something like this. Rubin will observe a patch of the night sky, and then it'll come back to it in a few days. But in the meantime, we shadow it by imaging the same patch of the sky with DECAM and find out that there was something that showed up in our image that wasn't in Rubin's. Like it could be a very young supernova, which is really cool. So we release the info to other astronomers using the brokers mentioned earlier. And other groups turn their glass and hardware on this exciting new object, and they get great data, and you can thoroughly study this young supernova. So Rubin surveying frequently combined with our shadowing lets us catch objects like supernovae incredibly early. And that's really exciting. So the only thing that could make this cooler is if we could get robots involved somehow, and I'm pleased to report that we can, and it's not AI related. So Rachel, Carrie, Katarzyna, and myself work at the Las Cumbres Observatory, which is a network of robotic telescopes controlled from right here in Santa Barbara. And we have telescopes in every time zone, basically. And so the second Rubin alerts us to a new discovery, our network of robotic telescopes can automatically point itself at the target no matter the time of day. Our motto is, we keep you in the dark, because I guess you could say the sun always sets on the LCO empire. We have developed these awesome tools like the Supernova Exchange, which allow us to control the entire network from like your phone. And we've hooked them up to listen to alerts directly from Rubin. So as soon as Rubin discovers something, if it's interesting, we have a whole army of robots that are going to go right after it. So once we get the notice of a new transient, we'll trigger, and our robotic telescopes handle the rest. So this is a simulation of one of the LCO telescopes pointing itself at a target and then following the target on its own across the sky. And the telescopes do everything. They figure out weather issues and data acquisition and everything in between to get the data and get it fast. So we can add our own data back to the alert streams, giving other teams the info they need to decide whether or not to follow the object or point their telescope elsewhere. But LCO shows that Rubin isn't the only thing that's looking at the sky, which brings us to the final part of our conversation with Rubin, which is what it can do with the information we give it. So by listening to Rubin, we can make discoveries faster than ever before. But if we can talk back to Rubin, we can unlock a whole new superpower, the ability to hunt down incredibly rare events like kilonovae. So let's have a quick intro to kilonovae, because they're not exactly household names. So if you take two suns, like our sun, and crush them down to the size of a city, furiously, to make two neutron stars, Stars so dense that their protons and electrons have been forced together in a goop of neutrons. Now take those two neutron stars and smash them together like a toddler playing with their toys in a sandbox. And the resulting explosion that you get is 1,000 times bigger than a nova, and it ripples space and time all the way out here at Earth, pretty much no matter where in the universe it is. And we have this amazing detector set up called LIGO to listen to these cosmic ripples, which are called gravitational waves. And it tells us where in the sky it came from so we can hunt down the explosion that caused it. So this is LIGO, and the way it works is it has these two huge arms, and there's a laser that goes up and down each one, and they meet in the middle. And it's in this right angle because if there's a wave coming in one direction, like rippling space itself, it'll cause one of the arms to shrink and the other to grow, and that messes up the lasers. And that's how it knows when space-time itself is wobbling. It's one of the most amazing things ever, and I'm not really doing a good job of selling how mind-bogglingly crazy this thing is. But when it does it, it uses this other amazing technology called email. And it sends us an alert. And this alert has all this information about where in the sky it thinks it came from and how far away it thinks it is, and whether or not it thinks there's a neutron star, or whether or not there's a mass gap between the two objects, or whether or not it was a truck driving by, which happens a lot. It sounds funny, but this thing is that sensitive. It's measuring a mirror changing over a distance like a billion times smaller than a human hair. No, many times smaller than that. But it's like the width of a proton, basically. I don't know how many protons are in a human hair. So it's measuring this incredibly small thing, so it can be disrupted by the wing beat of a butterfly in the chamber or a truck driving by a mile away. It's pretty crazy. So it gives us these regions, and then we have to go hunt it down. So that's what we did in 2017. It let us know of a neutron star merger, and somewhere in the universe, a galaxy got a new little star. So this tiny little dot is the kilonova, and this slightly larger dot is the galaxy. And it's really hard to find this. We got really lucky in finding it with the follow-up, because the universe looks like this, and you have to look at all these little dots, and every single one of them could be a candidate, basically, for having this object. And so it's a huge challenge. Now, the problem is like trying to find a needle in a haystack made entirely of needles, or like finding one specific grain of sand on the beach. So we get this map, and while from LIGO it looks something like this, and it shows us where in the sky it thinks it is, but while our field is really small, like this is the Hubble Deep Field, that image that I showed, and then this is it compared to the moon. So if we want to point telescopes like Hubble at it, it would take us forever to search the whole area. Rubin can do it much, much faster than we can because it's so big. So we tell Rubin where to go, and that there's a kilonova in this area, and it searches. So let's put that in perspective. This is a gravitational wave localization from a recent event. And this was a bunch of surveys attempts to fill in the area. And you can see many of them had dozens and dozens of pointings. And it took weeks to fill out all this data. Rubin would do it in like 45 minutes. And that's the difference between finding the kilonova within hours of explosion and simply not finding it at all. And using Rubin like this isn't limited to kilonova and gravitational waves. We can trigger based on detections in X-rays, gamma rays, and anything across the electromagnetic spectrum. So to recap, Rubin is going to be a very powerful extragalactic discovery engine, increasing our sample of astrophysical transients by multiple orders of magnitude in just a few years. We're going to follow up on its discoveries using our own instruments, and taking detailed data when Rubin can't, and turning discoveries into astrophysics breakthroughs. And finally, we will use target of opportunity triggers based on multi-messenger information like gravitational waves to hunt down some of the most extreme and rare events in the universe. I don't know about you guys, but I'm excited for extragalactic science with the Rubin Observatory. And up next, we're going to have Carrie Holt, who's going to tell us about solar system science with Rubin.
All right, great. Thank you so much. Yeah, so my name's Carrie Holt, and today I'm going to talk to you about all the amazing solar system science that we think we're going to be able to do with Rubin. First, I'm just going to explain why we care about studying things so close to home compared to giant explosions that are super cool that Joseph just talked about. And it really comes down to understanding the origins of our own solar system. So our solar system formed from gas and dust that condensed together to form the planets, just like Katarzyna showed earlier of the disks that we see in the Milky Way. But I wasn't there, we weren't there, we don't know exactly how it formed, so we need clues to understand how did our solar system form, what has happened since then to get us to where we are today. So small bodies, and when I say small bodies, I mean like comets, asteroids, small rocks, these can give insight into that. And this is because small bodies are leftovers from planet formation. So these small bodies are reflective of the composition and temperature of their formation region. So in this image here, you can see all the gas and dust at the top, and these small bodies are formed from that. Compared to the planets, there's relatively little change because they're much smaller. So we can then use them to probe the conditions of the early solar system. And however, most of these small bodies are very small or very far away, which makes them much fainter and then difficult to observe. So we already know of hundreds and thousands of asteroids and comets, but there are still millions more left undiscovered. Here's an example of a very small faint comet that you can barely see in that, but it's there, just to give you an idea of how faint this is. And this is not faint in the world of Rubin. So fortunately, we have Rubin, which is going to be a small body discovery machine. It's significantly larger than the past survey telescopes that we've used, so it can observe objects that are very faint and very far away. And observing them about every 3 days allows us to link these objects together to understand their orbits and then also do long-term analysis. And I should mention here, you can see this wonderful comet in the background during construction, which is something that I'm particularly interested in, is studying comets that are very far away and seeing how they change. Related to that, we just told you that Rubin is looking at the changing sky. And how do small bodies fit into that? They're changing because they're moving. So everywhere they are, they're always going to be one of those changing things. So the Rubin pipeline will be able to separate the moving objects from other transients. And then the solar system pipeline will be able to quickly link observations of the same object together. Here's an example of an asteroid moving across the field. And I'm happy to share with you all that Rubin has already made solar system discoveries. So I'm going to show you another video from First Look that you've seen some of the other ones so far. This one has to do with all the amazing asteroids that Rubin discovered just with the First Look data. So that's an example of an asteroid moving in the Rubin field. And these are all different asteroids. And so you can see these have quickly added up, and by the time we get through 7 nights, Rubin discovered over 7,000 new asteroids. Or sorry, not 7, 2,000. 7 nights, 2,000. And this carved out this little piece of the asteroid belt that you can see here, almost looking sort of like a spotlight coming out from Earth. And as the Earth rotates around the sun, it's going to be able to observe these objects in the full, all around our solar system. And beyond just these new discoveries, we've actually already started doing science with this. So one of my colleagues who actually used to be a postdoc at Las Cumbres Observatory was able to look at some of the First Look data and see if we can learn anything about these new asteroid discoveries. So what you're seeing here is that first look image that Rachel showed earlier, but you might see something a little different, and that's these colorful streaks looking things across the image. These are not streaks, these are actually a bunch of tiny dots, a bunch of observations of asteroids crossing over the field of view. And they're different colors because they are taken in different filters, different filters as they go across. So more blue, green, and red is how they were colored for the main image. And so what we can do with that is look at all the individual brightness measurements of these asteroids and plot them over time like this, and we get these interesting shapes. And this has to do with how the asteroid is spinning and the light being reflected off the asteroid. And the variability is because of the asteroid's shape. So we notice that we have this sort of double peak. It's hard to notice just looking at it, but there's this double peak pattern. And if we kind of fold it on top of itself, let's say right here, about like for every double peak, we can then fold it on top of itself and get this rotational period, this rotational light curve. So this tells us that this new asteroid here rotates every 1.1 hours. And we were able to do this with over 75 new asteroids and get 75 new rotation periods, which is just incredible, with only the first look data, which is very impressive. Not only that, but we were able to discover some extremely fast rotators. And by extremely fast, you can see here on the left, this is the fastest spinning asteroid known to date. So this asteroid is 430 meters, which is it's smaller than Stern's Wharf, actually, in diameter. And it is spinning every 1.8 minutes, every 112 seconds, which is incredibly fast. And that's not just impressive because it is spinning fast, it's also because it is a main belt asteroid, and a lot of these fast rotators that we know of so far are close to Earth, are near Earth asteroids. So this is exciting to hopefully we'll be able to see even more of these in the future. So just like Rachel said, again with these more discoveries, one of the pillars is to take a census or inventory of the solar system. So fortunately, we are going to be able to observe so many more of all these objects. So some of the groups include near-Earth objects or asteroids crossing into near Earth's orbit, main belt asteroids in the asteroid main belt, Jupiter Trojans, which are gravitationally bound in Jupiter's orbit, trans-Neptunian objects, which are beyond the orbit of Jupiter in the Kuiper belt, and comets, my favorite, and also some interstellar objects. So overall, Rubin will discover 10 times more asteroids and comets than what we know of so far, which, like I said, will be over 6 million objects. And fortunately, we're going to be able to have many of these discoveries in the first year of the survey. So this is a simulation showing the new objects being discovered. So the left is a sort of top view, and the right is a side view, and the different colors match the different groups of objects. But you can see in only a year, we make almost a full circle around and have over 3 million discoveries, which is very exciting. Not only will we have more of these objects that we already know about, we're going to have more of the weirder objects, which I think is one of the things I'm excited about as well. So this includes near-sun objects. We have near-Earth objects, but some things that are even closer to the sun, like this object here, which is an object whose orbit is completely inside of the orbit of Venus. Hopefully discover some multi-object systems, so binary asteroids, asteroids that are rotating around each other. Objects that are on unusual or extreme orbits, so this is several Sedna-like objects. So just to tell you how extreme this orbit is, that little blue dot, that is our known solar system. So that's how much bigger it is. Small Earth impactors, these are that we will be able to discover these streaks these smaller dim impactors way earlier than we have in the past, which means we can be prepared for them to get better observations, or obviously if there's something we need to worry about, we'll have more warning time. And lastly, interstellar objects, which is also one of my favorite things. These are objects that are formed in other star systems that are traveling through our own solar system. And you might have heard that there was a new interstellar object recently, and I'm also happy to tell you that Rubin was able to observe this object, so even more science already coming out of Rubin before the survey starts. So interstellar object 3I Atlas, it was discovered by the Atlas survey in July 1st. The Rubin team, quickly after discovery, was able to start investigating and found that during commissioning, they already acquired 10 serendipitous observations, which then meant that it had the earliest, highest resolution images of the object. So this is a picture of that, and this is from a whole 10 days earlier before discovery. So this says that if the survey had started, Rubin likely would have been the first to discover this object, which is promising for the future, and hopefully we discover many more. And with many observations, we can also just start to characterize these objects individually and the populations that they're in to learn more about how our solar system formed. So this includes things like the orbit. When we characterize the orbit, it gives us an idea of its dynamical history and where the objects are from, how did their orbit migrate to where it is now. We can get an idea of color, which gives us an idea of what they're made of or their composition. Their spin or their shape, which we can get from those rotational period light curves that I showed you before. This can tell us about some of the collisional history and the internal structure of these objects. And we can also learn a little bit more about size, which can give us an idea of the formation history as well. How big are the different pebbles coming together? And this is just for our objects that are asteroids that are not active. These active objects, like comets, have a whole other resource to look into. So in addition to discoveries, Rubin's going to be able to alert us to changing features of known objects. So just like Joseph said, with being alerted to different supernovae, we can also be alerted to different things that are happening on different solar system objects as well. This includes color changes. We might be able to see if something changes colors unexpectedly. If a comet or something fragments, these outbursts that happen frequently in comets, just a bright increase in brightness that then fades away. You might have remembered this sort of horned comet that was due to an outburst a few years ago. Or any sort of dimming that is unexpected, like this comet had a gradual dimming over about a week. So that's to say, whether we are observing new objects, all these discoveries, or being alerted to things for us to point our new telescopes at, Rubin has the potential to transform how we view the solar system for sure. So stay tuned. Thank you so much. And I will invite the other speakers to come up so that we can do a Q&A.
Well, great job to all of our speakers. Thank you three very much indeed. And with that, folks, we'd like to throw the floor open for questions. Please wait for the microphone to get to you before you speak so that everybody can hear. And I see we have one already. Please go ahead.
Thank you. This is wonderfully exciting, and the presentations were exciting as well. 3 questions, real quick ones. What is it about those areas that are going to be deep drilled that makes them especially interesting? How were they chosen? Where's the power coming from to power the telescope, given that it's intentionally in the middle of nowhere? And please tell us something about Vera Rubin, since she was an astonishing astronomer. Thank you.
Okay, thank you. That's great. So you were first to mention the deep drilling fields. Why don't...
More about the deep drill fields than
I don't know.
I actually don't know why they were chosen either. I don't know why I don't know why the specific regions were chosen.
Oh, okay. Okay, I can speak to a little bit, first of all. The deep drilling fields, the Rubin Observatory went through a very complicated process of figuring out where in the sky is most optimal to look. And of course, everybody in astronomy went, my bit, that bit over there. No, that one over there. Which could have been an argument, but in fact, the project managed to orchestrate a community-driven process over the course of about 10 years to figure out the optimum survey strategy. And part of that is a very complicated survey strategy process, so that some areas of sky get really intensive coverage, and it goes very, very deep. That is, it gets to much, much fainter objects than it will normally do over the whole sky. Those we call the deep drilling fields. And those were chosen to be usually over specific areas that have been observed by other facilities as well, to give us continuity over some of the observations that have been made, for example, in different wavelengths, so that we get data not only in the optical band passes that Rubin will follow, but also in infrared wavelengths. Some of the other fields have been studied for various different cosmological structures. And I think that those are the main fields. So that was kind of part of the process of coming to this very grand survey strategy. And you mentioned about how Rubin is powered. I don't actually know, I have to confess. Lisa, do you? Oh, excellent.
I mean, Rubin is powered by the various power plants they have there, but they are putting in acres of solar panels in Chile to power. They're already powering the Gemini Observatory, and they have been approved. They're putting in a whole other huge thing. Rubin uses a lot of power, so it's not going to be all of it right away, but they're making a real effort to have renewable energy for it, which is pretty cool. Sorry.
Thank you, that's great to hear. And for Vera Rubin herself was actually a pioneer in cosmology. So, Joseph, something you feel comfortable speaking to? There we go.
Absolutely. The classic Vera Rubin discovery was her work with galaxy rotation curves. We kind of take dark matter for granted today, but it was not that long ago that we had really no idea it was out there. And Vera Rubin pioneered her method of looking at how fast galaxies were rotating. So when you have matter that's rotating around it's gravitationally bound to an object and rotating around it, there's a maximum speed it can achieve. If it goes any faster, it'll fly off. And so galaxies should follow this rule because they're all orbiting this big gravitational potential. And so she looked at hundreds of these galaxies and measured how fast they were rotating and realized they were moving way too fast to have the mass that they appeared to have. Some people had sort of looked at this before, but she was the one that got these pristine data sets to prove it was not some sort of data artifact and pushed the idea that there is this hidden matter that was gravitationally interacting but not interacting with light. And she is basically entirely responsible for dark matter becoming the accepted mainstream idea that we know of it today. And now her discovery has been sort of proven irrefutably over and over again with the cosmic microwave background, baryonic acoustic oscillations, and it's one of the greatest achievements in scientific history, and the observatory is exceptionally well named.
So,
Wonderful, thanks.
yeah.
Oh, over there, thank
Yeah,
you.
sorry. Two questions. Joseph, you mentioned that you're looking for some very rare kind of supernova things. Maybe you could say something about that. And then I had another general question. So when it's doing these all-sky surveys over a big area, so it's able to give data to each of your missions simultaneously? Is that it? Okay, good. But okay.
Okay, yes, let me take that one first. Having done this great complicated observing strategy will tell us exactly where to point. And as you saw from some of the sky maps that a scientist showed, it will point everywhere in the visible southern sky at some point. So yes, everybody gets some science out, which is why it's such a huge boost to all of astronomy. So for the cosmology?
So I study rare supernova subclasses. The two that I focus on, one of them is called Type 2b supernovae. So we organize supernovae based on whether or not they have hydrogen in their spectrum or not. So type 1s don't, type 2s do. And basically for type 2s, we think that there's some massive star and they lose some of their hydrogen over time and explode. And we can tell how much hydrogen is left. And previously we thought either they have a lot of hydrogen because they didn't lose much, or they lose all of it because why wouldn't they? But only in the last couple decades, we've learned that there are these incredibly specific rare objects that they have the teeniest little amount of hydrogen, like a sprinkling, like a dust thing. And that's just very interesting because it allows us to look deeper into the star right before it explodes. It gives us some insight into the mechanisms that cause them to blow up. And we only have like 30 of them that have like really good data. And Rubin is definitely going to give us hundreds of thousands, which is crazy. And that's just one rare subclass. There's all sorts of others, supernovae that have magnetar central engines, like this neutron stars with very powerful magnetic fields blowing them up from the inside. I could go on, but Rubin's going to give us all this amazing stuff for all these rare and bizarre objects. Thank you.
Over there.
Well, I'm hearing about a program that's going to last 10 years, and the program that lasts 10 years is going to require very stable funding sources. I see most of this funding coming from government agencies, and to put it most politely, we're seeing a lot of instability in research funding. How secure is the funding for the Rubin project?
I think they might shoot me if I said it was 100% secure, so I don't want to say that. My understanding is that there is money allocated for the operations of the Rubin Observatory, and for the foreseeable future, that has been secured as much as anything is in government funding these days. What there is also is a process by which the international community were able to apply to get rights to access the data from Rubin. And in return for that, they had to provide something in kind to the American community. That took the form of running data centers, providing telescope time, providing support for various operational procedures. So it's not uniquely on just the US government to support this great program. It is supported also around the world, and that's at the government agency level. Now, that what is not currently supported is to do actual science in the US with the data from Rubin. That is considered separate. That is something that scientists like myself and everybody you see here have to apply for on a more or less annual basis. And it's really that funding that we are most concerned about, because in order to realize all of the science that we've talked about tonight, we are going to have to employ fantastic scientists like the ones you see right here. And that is going to be the key to actually unlocking everything we just talked about.
I've got a couple of questions. One is how Rubin will change the way LCO operates. And also how scientists operate, because you go from a data poor regime into where there is just this overload of data, and explain how your lives will change and how the operation of LCO, how their priorities have changed because of this coming online.
Fascinating topic. So I think all of us could speak to that. Katarzyna.
Well, it already has changed my life, because we have a platform that we use for following up microlensing events with LCO telescopes, and not only LCO telescopes. And because we were preparing for Rubin to start, and for this tremendous amount of information coming to us every night, we had to rebuild our system. a little bit. We had also, and that is Rachel's, a lot of Rachel's time was to bring in other observatories to be capable to work in a similar way that LCO is working. For example, SOAR telescope, which is a 4-meter telescope, a CFHT, another medium scale telescope. Also, a Blanco telescope, which is the telescope that Joseph mentioned. It's a another 4-meter telescope. Pretty much, we need all of the 4-meter telescopes to do any follow-up for Rubin, because it's going to go so. He's going to observe such faint objects. And I will just let other people talk, because I can talk about this for hours again.
I think Lisa would like to weigh in.
Yeah. What I was going to say was, these are great questions, and what I'd like to do is invite people, the speakers, to come down here, and then everybody else to come over here if they want, and we keep having these conversations. And I'll just say LCO was built to follow up the Rubin Observatory, so we're ready. Yeah, no, I'd like to thank everybody, the speakers. It was fantastic what you did once again. But yeah. And we are happy to talk to people over here.